the speaker.
Just wait a second.
Okay.
Got
So
it.
Ilya, you can go.
Okay, so yeah, thank you very much for this invitation, and it's my big pleasure. So actually, I expected that I would be giving a talk in Russian. So, but Georgi told me that it's an international seminar, so the talks are in English. Well, okay, so let me start. But first, I have prepared some slides, and I would like to share them. I have to understand how to do this. Share screen. Okay, I have some rights. Yes, okay, I found the file. Share. Good. Just wait a moment. And yes, while I'm preparing everything, so I also warned Georgi that, well, I'm at home now, as many of you probably, and sometimes I have some problems with the internet connection. So this means if I disappear, so that does mean that I left. Just please wait for, well, 5 minutes or 3 minutes, and I will reconnect. So this happens from time to time. Just wait a moment. Now here. So I don't know. So is the screen visible? So
Yes. Yeah, it's okay.
it's okay. Yes. I don't know. So I cannot see myself. So how it looks like, to be honest. No,
Yes. Yes, it's okay. Yeah.
It's okay. Yes. Yeah. Now I would like also to tune that I see the speakers if someone would like to talk to me. Okay. Good. So let me start. I would like to talk about the so-called Levy-driven transport equation. And this is a joint work with my student, Lena Hartmann. And so, well, the talk will be not given in the full generality, and my goal is to give some ideas and so present the qualitative results. And of course, well, generalizations are possible and numerous, and we can discuss them also later. So what is the main idea? So the main idea is that we consider, in many problems of nature, let's start it so very generally. So one can consider or describe some effects or some physical processes by advection diffusion equations. So, and advection and diffusion equation look like this. So, and we consider a linear one. So this is a parabolic equation of this form, so partial derivative with respect to time. And just for simplicity, let me assume that everything here is even one-dimensional. So which is of course not necessary, but just for simplicity at the moment. So, and the equation looks like this. So u, so the unknown function, so is very often referred to as a concentration of some contaminant of a tracer. For example, you put some gift into the water and it then transferred, so in the water with certain speed and with certain diffusivity. And the equation is given by this. So if you would like to calculate the concentration of the tracer, so the important parameters are R. So A, so here, times the gradient of U, so gradient is the special gradient. So this is a random velocity, or random or not random velocity field, with which the contaminant at point X, or so in this case, it doesn't depend on, well, A doesn't depend on X, it can depend on X, it can depend on T, is transferred. So B is the maybe random dissipation. So this is the rate with which the contaminant will go down or disappear from the system. So C is a random source, and D Laplace operator is the random diffusivity. So this means, roughly speaking, what you expect if you put some contaminant into the water. So now I plot a two-dimensional picture. So then, well, infinitesimally, well, it will go, roughly speaking, so with some velocity A into direction A. So A is a velocity here, so is a vector velocity. It will diffuse with a diffusivity matrix B, so it will disappear with some rate and so on and so on. So this is a usual equation. And what we will consider, you consider even a simple equation. so without a diffusive part, so which can be added later, so if you will like to. And we consider the so-called equation, the transport
Sorry,
equation, the
Ilya,
equation for the poor.
Ilya,
Yes.
can I interrupt you?
Yes.
Just for a moment, am I right that U can be considered as a density?
Yes, can be considered
Yeah.
as a density. So it depends on
Then,
the interpretation.
if we have only a gradient, then it will be just motion of this density along some trajectories of some deterministic flow.
I will be speaking about this. So this is exactly the case.
Okay.
So
Okay.
yes,
Yes,
of course, of course.
Mhm.
So exactly. So, but you just go 3 slides so faster than I. So let us consider the very simple equation. So just to recall you. So let's remove all the unnecessary parts. So the diffusivity part and the source and the dissipation. Consider the transport equation even with a constant velocity here.
Mhm.
And then the solution can be found immediately, roughly speaking. So if F is the initial concentration or initial density or as an initial condition, so any of them, so then the solution is just given by X, so your point X plus AT. As Andrei just correctly said, so what you see is that the initial condition, so initial concentration just moves, well, if A is positive, so it moves into some direction, so with a constant velocity A. And how to prove this? Well, you just substitute, calculate the derivatives, and you see that the equation is satisfied. Good. Now we can go on and we can consider this more general equation, so where the coefficient or instant and infinitesimal velocity field depends on t and x, and then it turns out, and it is well known, so that such an equation can be solved indeed with the so-called method of characteristics. So this means that the solution it can be shown the solution is constant along the solutions of the so-called characteristic ordinary differential equation. So how to do this? Well, in order to solve this equation now with, well, initial condition F, distribution F, what you do? So you write down the characteristic equation, so which is an non-autonomous, well, if you have a dependence on T, non-autonomous ODE. So you have to invert here, so the sign, so to minus. So, and then it turns out that along, so if you assume that all coefficients are nice, so Lipschitz continuous and smooth, so bounded and so on. So then there is a global solution of this ODE, which actually defines a flow, so as a function of x. So this means phi t, so maps, well, r to r, so as a function of x, or rd to rd. So under certain conditions, so smoothly, so and smoothness, you can get everything what you like. So then the following relation holds. So, and this means that immediately you can write down the solution of the solution u, so by applying the inverse mapping, so to phi, and the solution is given by this. So u of tx is the initial condition applied to the inverse flow of the so generated by solutions of these characteristic equations. So, as the proof is also sort of straightforward, you just take this function, you differentiate it with respect to time, and due to the choice of your functions of your function phi, and so on, so you see that these solutions of this derivative with respect to time is identically zero. Good. Good. So this is a deterministic theory, and everything is known. And now what we are going to do, or so what you can do next. What you can do next is you can ask yourself what happens if the velocity field is random. So this means, and this means that you should consider not the ordinary, well, deterministic equation, but you have to consider some random equation, and well, first assumption or first idea is that you have to assume that your velocity field is now a sort of, well, white noise in the following sense. So actually, well, let me write an equation. So we would like to consider equation du, maybe later. So is nabla of u, okay, no, not nabla of u, so let me correct. So let me write a of x, nabla u, and here I would like to write, let me write it physically. So I would like, because I do not want to say exactly so what is going on at the moment, because it has to be made precise. So let me take Newtonian notation. So u is the derivative with respect, so u dot is derivative with respect to the time. So now a is a function. Now you have nabla u, and here, for example, you put Brownian motion, well, white noise. So you take and let's not discuss what it means at the moment. So, but well, physically, so this is a goal, how to understand. So, and if we would like, which is, well, actually, this theory is also known, and I just repeat sort of motivation. So we would like to give meaning to an equation of this type. And how to do this physically? So if you consider this equation from the physical point of view, so then, of course, well, physically, there is no Brownian motion. Physically, there is no white noise because everything is smooth, and the Brownian motion is just some mathematical idealization of some processes and so on. So this means a physical approach to this equation would be the following. So, well, let us consider our driving Brownian motion, so which, as we know, does not exist in nature. And let us approximate it. So, okay, let me pass to this picture immediately. By some smooth or piecewise smooth functions. So these functions, so these approximations are called Wong-Sakai approximations, and they are due to, maybe firstly considered by the paper by Wong-Sakai in 1965, if I'm not mistaken. So it is Wong and Sakai. So what is the idea? Okay, we say that, well, since we have no Brownian motion in our real life, so let us, instead of a Brownian motion, W, consider its smooth or piecewise smooth approximation, and it is given here. So I just take an equidistant partition of the time interval, and I just connect so the points lying on the blue trajectory by this red segments, and I could get a very nice trajectory. And now let us put it formally into my transport equation, which I would like to consider. And now you see, so that this is just an random, well, it's just an random transport equation, which can be solved pathwise because the derivatives, so Wn dot, so these are piecewise constant functions. So this means we can solve this equation on each time interval, and then glue together so the solutions to get the global solution. So, and of course, well, if you do this, so then we can somehow we understand so that the method of characteristics should also work in this situation in order to get solution. And what is the method of characteristics? Well, since this ODE, so each approximation is just a random, well-behaved, so classical transport equation, the characteristics equation of it is a random, non-autonomous ordinary differential equation, so which looks like this. So for each n, I just write down my ODE, and here, well, we have this derivative of the Brownian motion, so of the approximations, but this is a piecewise constant function. So it can be solved uniquely and so classically. And of course, well, I can write this integral, so not as an integral with respect to ds, but well, if you like, it's a Stieltjes integral or piecewise Riemann integral. So you can write it like this. So this means the deterministic classical theory tells us that the solution un is just given explicitly by the following formula. So I solve this characteristics equation for each n, take the inverse, so put it into the initial condition, so that's it. Good. Now, how to pass to the limit? And passing to the limit, so this is also a classical theory. So we know that if we have, well, let me put it here. So if we have a sequence of ODEs of this type, where WNs are smooth or well-behaved, continuous, or bounded variation approximations of a Brownian motion, then by passing to the limit, we do not go or we do not converge to a Ito integral or to an Ito SDE, but it is well known that we converge to the Stratonovich SDE. So, and this means by passing to the limit here, so we arrived to the limiting characteristics equation, which is a solution of a Stratonovich ordinary differential equation for the flow. And then, well, you can apply the usual theory and so on. So actually, this is a theory. So, and it can be found in, well, there are books about this in the Gaussian case. So, and essentially, so you should refer to Kunita, so as his paper and lecture notes, and finally the book in 1997, and certain, well, more complicated situations were considered, so where coefficients are not smooth enough and so on, were considered by Flandoli in 2011 in lecture notes of mathematics. So what you get is that in order to solve the equation, transport equation, so random transport equation, with the help of method of characteristics, you have to write it in the sense of the Stratonovich integration. So first of all, and it was shown that if you use here Ito integration, then the problem is not well posed, so it's ill posed. And then the solution is given by the formula. So UTx, Tx is f of phi minus 1. So where is t? So t of x, where this is now a stochastic flow of, well, if the functions are fine, so of diffeomorphisms. Good. So this is, so to say, known. And now what we are going to do, so essentially we are going to consider the case of Levy-driven processes. So of Levy-driven equations. So this means what we are going to do, we are going to generalize, so or to understand how this equation can be solved if instead of the Brownian motion here, I write some jump or pure jump or any Levy process. And this is, of course, not the whole, the full generality. You can consider semi-martingales and so on, but in order to understand the ideas, so let us consider the Levy-driven case. So, okay, let me go to the slide. So, because, so let me, well, I do not repeat what a Levy process is here. So for this audience, but so Levy process, just generally. So why Levy processes? So Levy process is, as we know, a process with independent stationary increments. So well, starting at 0 is the technical part. So the only continuous Levy process is a Brownian motion with drift. So all other Levy processes, it can be proven or it can be considered as a part of definition. So they are Cadillac. So they have sort of regular trajectories, but they can have infinitely many jumps. Of course, the number of jumps is countable or finitely countable on each finite time interval. And so why Levy processes? Because say from the point of view of applications or from the point of view of physics, for example, so Levy process is a second best choice in models where the Brownian motion doesn't work. So, and we know that Brownian motion is a Gaussian process and it has a lot of good process properties, but on the other hand, it has some restrictions. For example, well, continuity, for example, or you have exponentially light tails and so on. And if you would like to have models with jumps or with models with heavy tails, then the second best choice, as I say, so from the physical point of view, is a Levy process. Good. Let us now guess a solution. So I would like to solve now a transport equation. So ut equals to, say, a of x w, and here I write, okay, let me write here dot and here dot, and here I write a Levy process. It can be also a Brownian motion. I do not say now in what sense I understand the stochastic integral, so this will be one of the questions. So let us try to guess a solution from the previous heuristics. So, well, as I said, Levy processes are in general not continuous, but it does not forbid us to consider Wong-Zakai approximations or polygonal approximations. So we can even make so discontinuous trajectories smooth or continuous. So what I do, let me consider some partition of time. So let me consider some points, and then I just connect these points by segments. So then I get a continuous function. So of course, this continuous function, when I pass to the limit, it will behave very irregularly. So because if the process has a jump here, so then this function will, well, this segment will converge to a vertical segment, which is actually, well, not a function, yeah, so because it will be multi-valued and so on. So this means what we know that for each n, for each approximation, if I consider these trajectories, so this is a very nice, well-defined function, but passing to the limit, at least in the uniform topology, is problematic. So because of the jumps. So, but at least, well, in sense of finite dimensional distributions, convergence will hold so clearly. So this means these approximations are not as bad, but you have to be careful. So if you would like to consider them as processes. So now, so if I have these approximations in hand, let me consider a classical random transport equation. So this is what we already did. So I take for each n, I just write my approximation of the process L dot n. So, and I can solve this equation by the method of characteristics. Characteristics equation is again a non-autonomous ODE, so can be solved. So for each n larger than 1, clearly, so uniquely. So, and the solution of approximations is given. So now the question is, what happens when I pass to the limit? So because I have to guess the limit. And it turns out, well, that smart people already studied this, and passing to the limit gives us not the Stratonovich equation, but so to say, its equivalent or its counterpart in the case of jump processes. We get the so-called canonical or Marcus equation, which is denoted traditionally here by diamond. So Stratonovich is usually a circle, and Marcus equation is denoted by diamond, but some authors also use circle, and well, there is some misunderstanding in the literature sometimes. So people sometimes mix these processes. So, okay, so generally Marcus equations are not well, generally well known. And I would like to just to repeat, so very briefly, some of the properties. So how are they defined? And so how should we understand them? Well, canonical SDEs were introduced by Steve Marcus. And Steve Marcus, I think he works still in the United States. I think he's at the Brown University, but he's not a mathematician, so he's an engineer. And I think his affiliation is electrotechnics department. So he introduced them in 1978. And actually, it is funny. So it was a paper, if I'm not mistaken, in IEEE. So, you know, this transactions of engineering, I forgot so how to explain this. So some transaction of engineering papers. So, And his goal was to consider, say, a Poisson process, a jump process, and write down an equation for which the chain rule, so this means the change of variables formula, holds true. So, and then you immediately arrive to this construction. Oh, so sorry, it's a typo. So okay, let me write DZS. So let me. So how do I understand Marcus or canonical equation? So we write an SDE in the following form. So phi t is the initial value, plus we have the usual Lebesgue part. So now we have a Gaussian part, which is understood in the sense of Stratonovich integration. And then we have to introduce here the jump part. And here I assume that Z is a pure jump process, pure jump Levy process. So this means for me, it is convenient to decompose the Levy process. So drift, deterministic drift goes here, Brownian part or Gaussian part goes here, and here we have only jumps. So, and then it is understood like this. So I rewrite it again. So this is the Lebesgue part. So the Stratonovich part, if all coefficients are smooth, is understood as an ether integral with respect to the Brownian motion, plus the so-called noise-induced drift, or Stratonovich correction term. And the diamond part is understood like this. Well, first of all, we have the Ito integration with respect to the pure jump Levy process in the usual sense. But then we have to add a correction term. And the correction term is a bit more complicated. So to understand the correction term, we do the following. Okay, so let me maybe put here into another slide. Oops, no. Just wait a moment. Background. Ah, yes. So it works. So in order to understand, so this means the main question for us is, how does this process jump the solution? So for example, you see, we have the following situation. So I have my Levy process, so Z, and it makes a jump at time tau of the size delta Z tau. So now I have my equation and assume that I can solve it. So, and now I write, it's convenient to me to plot everything in R2. So this is my equation. And now, so this is phi. And at time for phi tau minus, I arrive at some point. So I assume that my processes are Cadillac, of course. So just before the jump, we are, so R2, somewhere here. So tau minus. Well, and now the jump happens. And of course, well, when the driving process Z jumps, my solution should also jump somewhere. So this means after the jump of Z, I should get here and then continue. So if my process, for example, jump process is a compound Poisson. So the question is, how do I pass from here to there? So the answer is that in the Marcus setting, you should do the following. You see here, so the diffusion coefficient, well, it's not diffusion, but the volatility which acts on the jumps is a function alpha. So what I do is now I write down an supplementary ODE, which is a nonlinear ODE, which is of the following type. So this is D, well, it's now this phi. Say du is alpha, is my diffusion coefficient in front of Z, of phi, okay, of u times Z. U is on the interval 0, 1, so this is an artificial time, which does not, which doesn't have anything to do with our true time t. It's artificial time. And the initial condition phi of 0 is exactly my position before the jump. So, and now I solve this equation. So, and well, if everything is fine, so then, well, it's a nonlinear equation. So then I get some solution. So let me take another color. So red, for example. And now, well, you see, I can plot this solution. And for example, so this is my solution phi of u. And now, well, of course, it depends also on z. Yes, I have to write here delta z. Delta z top. So this is my jump time. So delta z top. And solving this equation, I get to some point. So, and this is the new position of my solution of the my solution of the Marcus equation. So this means in order to solve this Marcus ODE or SDE, sorry, you have to do the following. So, well, if there are no jumps, you just solve a usual Stratonovich SDE. If there is a jump, then at each point of the jump, you write down the artificial supplementary ODE of this type, solve it, and then you know, then you learn your new position. So after the jump of the premises Z, and then you put everything together, and so this is your solution. So this looks a bit strange, but actually this is a very natural construction. Yes, and yeah, and there are also two approaches to these canonical equations. So one approach is to write down the equation in this form, and this has been done initially by Marcus himself, and then there is a very good paper by Kurz, Pardue, and Prota in 1975, and they call it actually Stratonovich for semi-martingales, and they work in this setting, so to say, and prove that there are solutions and properties and so on. So there are also another very convenient writing of this equation due to Kunita, which we will use in this talk. So, well, it turns out that you can write down the canonical Marcus SDE as a, well, classical Ito stochastic differential equation with respect to a, well, not a Levi process in the sense of Prota, book of Prota, but in the sense of integral with respect to a Poisson random measure. So this means what we do is, so if we decompose our process, pure jump process Z, we take the Levi-Ito decomposition into sum of compensated small jumps and possibly large jumps. So then equivalently, the equation, canonical equation, can be written as this. Well, this is a formal writing here. So this is what you write when you just would like to make things short, Stratonovich and here diamond. And then you have to understand it like this. Well, Stratonovich part is the usual part, and here the jump part is the following. And this is exactly what I just explained above. So, well, we have some compensating terms, but so what are the jumps? And the jumps are given here. So, for example, you look at this formula. If the process Z jumps, well, this means the Poisson random measure has a jump. So then what we have to do, we have to write down the supplementary equation, solve it on the time, on the artificial time 0, 1. We denote the end point of the solution by, so I write bold E. So this is the exponential mapping of the flow. So bold E is not the exponent, bold E is the value of this solution at time 1, of the artificial time 1. So, and I consider this guy as a mapping. Well, actually, this is two-dimensional. So this is Z and X, and I get here this value Z, which depends on Z and X. So I take this function, which is, well, is some nonlinear function. Yes, and well, this is my jump. This is my jump. Good. So looks a bit long and maybe complicated, and indeed, so I will show you later. If you work with Marcus equations, so this is a bit messy. If you would like to write down everything, because you see, so well, the Lebesgue part is okay. So the Stratonovich part gives you 2 terms, and the jump part gives you 3 terms. So this means the equation somehow, well, explodes in terms of notation. So what are good properties of the Marcus equation? So why do we like them? Well, first of all, it turns out that if we consider the Wong-Sakai approximations of our original equation, so this means let us consider a random ODE where I write here the Wong-Sakai approximations of the Brownian motion and Wong-Sakai approximations of the Levy process, which I explained before. I solve this equation. Now, passing to the limit gives you that these approximations, at least, well, in the sense of finite convergence of finite dimensional distributions, converge to the solutions of this of the canonical Marcus equation. So this means, you see, so our goal was to solve the transport equation. So considering this intuition, so tells us that the choice of the Marcus equation for the as a characteristics equation is the right choice. So this is one nice property. So this is the first one, very good property. And the second property is as in the case of Stratonovich equations, the chain rule or the Ito formula coincides, well, formally of course, with the Newton-Leibniz formula of the classical calculus. So this means formally, and well, I have to repeat it many times, if I take a good function f, some C2 function, and I apply f to my phi, so to the solution of the Marcus equation, then formally I can write it like, so the change of the variables formula looks like a usual change of variables formula, so the classical calculus. But you have to be careful. Well, this is not a problem here, so because Stratonovich integrals are well defined, so and so on. So you can define it with the limit of Riemannian sums, for example. But this part, you should be here more careful. So you have to understand that the jump of the process f of phi, so which is exactly the jump of this integral, you have to give meaning to this integral here. So the jump of this integral is exactly the following. So this is f applied to the, well, my supplementary Marcus equation. So with the initial point phi t minus, so which depends on the jump size, minus that. And now, well, you see here, so this is just a deterministic formula, well, omega wise for each jump, for each initial value. And applying the Newton-Leibniz formula to this function, to the function e, gives you the following. So you just differentiate it, and you see, so that this is, well, what is this? So this is f over, it was phi of 1, 5t minus, minus f of phi 0, 5t minus. Yeah. So this is, you see, so this is exactly the Newton-Leibniz formula. So you have to differentiate it with respect to the artificial time u, and then you get the following representation. So this is how you should understand this jump. So, but it works perfectly. So at least, well, formally you can really write, so work with Marcus equations if they were just usual equations, differential equations. Good. So, and now let me, sorry. Yes, and now let me solve the stochastic transport equation. And before going into so more general situation, let me consider just a very, very simple case. Actually, this is the only case when you can solve this equation, well, explicitly, roughly speaking. So, but I would like to show you so how it goes. So with the help of the theory which I introduced. So let Z be a one-dimensional Levy process. Let alpha, so alpha will be our infinitesimal velocity field. Let it be a non-zero, so a good non-zero function. And now I would like to solve this equation, which I formally write as, so dtu is alpha, now here the nabla u, and the diamond dz with the initial value f, well, which we should understand as follows. So we understand it as, so u of tx is the initial value of t. So, and now we have the usual usual Ito part. So I now write something similar to the ODEs. And now I have to add the jumps for each x here. And the jumps look like this. So in order to give solutions of this equation, so what happens? If my process z makes a jump, so then, of course, my solution is a function. I have to write down another artificial transport equation, parameterized by the jump size, parameterized by the new, okay, so, well, u was the time here, so it's abuse of notation. So by the new artificial time, which I denoted r, so from 1 to 0. And I solve this transport equation on this artificial time from 0 to 1. I denote the end value, so by bold E, and I write this equation like this. Good, so this is how I should understand it. But now let me solve it now. Okay, so this is actually the same. Yes, okay. So this is the same story. As I said, so there are two writings. So this one is, so to say, the way of dealing or treating these equations by Pardu-Prota and Kurs-Pardu-Prota and Marcus. And this is the way of writing of Kunita. So we write it as integrals with respect to the Poisson random measure of our Levy process Z. And now, okay, so let me get the solution in the simplest case, so as I wanted. So what I know is, or at least what I guess, in order to solve this equation, I have to write down the characteristics equation. So characteristics equations is a Marcus with C, so Marcus S D E. As in the case of Stratonovich equations, I can solve it with the help of the so-called Lamperti transform in dimension 1. So otherwise, well, it is more difficult to solve, so there are Frobenius conditions, but so usually, so they don't work. So this means I introduce a new function a, which is the integral of the function, so dy divided by alpha of y. So the method is known, actually. So I assume that everything is well defined. And now I apply the Ito formula or change of variables formula for the Marcus equation, which, as I know, looks like a conventional Newton-Leibniz formula. So in this case. So this means applying a to phi t gives me a minus the integral, so a prime of phi alpha dz, and a prime is exactly 1 divided by alpha. So this means this is exactly 1. And the integral, so dz of 0 to t s is exactly zt. So this means I get, so this the transformation, so gives me this formula. And this means that phi of t can be found as, so I apply the inverse function, a minus a to the power minus 1, well, the inverse function of a of x minus z here. And the inverse flow, because I need the inverse flow for my formula, it can be solved immediately, so I just denote this by y. So I solve this equation, and the inverse flow is given also explicitly by this. So this means my claim is now that if I consider a function u given by, so defined by this, so then my transport equation should be satisfied. So, and now we can check this readily check this. So what do we do? So, well, the initial condition is clear. So z of 0 is 0. So the initial condition is satisfied. So, and now you see, so here z is a, well, is a random process, but it doesn't depend. So there is no interplay with x. So I can differentiate with respect to x for each value of z. Differentiating this gives me this formula. So this is just straightforward calculation. And now I just apply the Ito formula for the Marcus SDEs. Well, I take a function f of a minus 1, of a of x plus dot. So this is my function, and I apply it to the process z. So z is well, also a solution of a trivial Marcus SDE. So I can apply this function to z in the sense of Marcus integration. So this means I have to differentiate with respect to z and write diamond dz. Differentiating with respect to dz gives me exactly this. And well, if I compare these two terms, I see that, well, compare. So this is exactly what I wanted. So this is my transport equation written in this diamond notation. Good. Okay, so this was, so to say, the, so sorry, I also have here numerical illustration prepared. Sorry, a numerical illustration. The numerical illustration tells me the following. Well, this is more or less just one of the very few examples when you can calculate something really explicitly. So even in terms of closed form formulae. So let me take the function alpha of this type. So how does it look like? So it is 1 and 1. And so then it, well, something like this, grows like x. Yes. Okay. So this is my function y. So z is some process. So the initial value will be taken. The initial concentration is just some bounded, well-defined, so good function. So this is my characteristics equation. A of x can be calculated explicitly, which is the arcus sine hyperbolicus. So the inverse function is sine hyperbolicus, and everything is known explicitly. So this means this is the explicit formula. So this is one of the rare situations when you get the answer. And this is now shows you how the equation evolves. So this is my process ZT. It makes some jumps. Well, and essentially, well, you can see that, well, it's sort of nonlinear, so because you have some strange dependence on x here, and f, well, f moves. Well, actually, you see, the problem is that you don't move f, but you move sine hyperbolicus of the argument moved by z. So this is how this random interaction with the so the randomness space and time interaction works in this situation. So this means our contaminant concentrations, so they go from the right to the from the right to the left, so depending on the jump size somehow, and they get sometimes more broad or more smooth or more thin, so to say, and so on. Well, it's not very easy to see here what happens here, but well, you can calculate everything if you like. Good. So, and now, well, I have 10 minutes, so, and I can briefly explain, so what is actually the goal, and what the methods are, and what is the result. And of course, well, you can already imagine, so, or understand, so what is going to happen now. So now I would like to consider a more general equation, So with the Lebesgue part, with the Brownian part, and with the diamond part. So on the gradient here, gradient there. So I wrote here that all functions are C for B. It's not necessary, just, well, you can assume that all functions are as good as they should be. So, and then what we are going to do is, we are going to consider the characteristics equation, Marcos characteristics equation, which now looks like this. Well, this is well-defined equation. So then it has a unique solution, which under certain conditions, and the conditions are, well, C4 is surely enough, but actually it should be C2 plus epsilon, C2 plus epsilon, and I think C3 plus epsilon here. So then there is a C2 flow. So then denote its inverse flow by phi t naught. So phi t naught is phi naught t, so the inverse. And now let me take u of tx is the initial value applied to this inverse flow. So then this is the unique solution of our equation. So this is the idea, and this is the statement. And now how to do this, how to prove this. In order to prove this, essentially, you see, since Marcos equations does not differ formally much from Stratonovich equations, what you can try to do is you take the argumentation by, or discussions by, say, Kunita for Stratonovich equations and try to repeat it for Marcos equations. And this indeed works. So, but what you have to do is you have to justify the steps. And for the justification of steps, you have to do certain work. And this is actually the technical work, which is, so to say, is the main technical part of this project. So, how to prove this? And essentially, what I'm repeating here, so this is the steps done by Kunita in the Gaussian situations, or in the case of continuous semi-martingales with parameter. So the proofs like this. So first of all, so it is convenient for me to pass to this, quasi multi-dimensional notation. So now let me denote L. So it will be a three-dimensional Levy process. So it's first coordinate t, second coordinate Brownian motion, and the third coordinate is a pure jump Levy process. I also denote f is a triple, so by coefficients. So this means I just would like to write this equation, at least for formally, as just to simplify the notation. So, and now, the steps done by Kunita are the following. Assume that we have shown that the inverse flow, so this is the inverse flow T naught, satisfies the following relation, the following equation. And here we have, so F is my triple of the coefficients. So L is a three-dimensional process. Everything is understood in the diamond notation. And this one is the gradient, so, or the, it's not good to write here gradient, sorry. So it should be, in dimension one, it's fine. So, but it should be the gradient matrix, or the Jacobi matrix, D of the forward flow to the power -1. So the inverse Jacobi matrix. And then I put in the inverse flow. So this is the forward flow, and this is the inverse flow. So assume that if we have shown this, so then we are done. So because we have the following. Since, the forward flow and the inverse flow satisfy the following relation. So this is the argument again by Kunita. So I differentiate, I have to write here D's, but yeah, so in dimension one, it's fine. So D is 1, so this means the inverse matrix. Yeah, it should be matrix, of course. Yeah, sorry for this. So inverse matrix is this. And then, well, what I do is, so I just substitute d minus 1. So yes, and now I take, so I define a function u, which is f of the inverse applied to the inverse flow. And now I apply the Ito formula, if I have the Ito formula. So now I use this relation. So this one, I pass, okay, to this line. And then, well, I know that f prime, so d psi is exactly, so d, yeah, okay, nabla, so it's, sorry. So nabla of f applied to f, so the composite function. And this, you see, so this is exactly my transport equation. So this means what I have to do, I have to show such a relation for the inverse flow. And in order to do this, we have to pass to a more general setting of a semi-martingales with parameter. So, and there is a literature about this, and I refer here to papers by Fujiwara Kunita, or for example, to a very nice paper by Kunita, 2004. So where this theory is developed. So this means what we have to do is we have to, so if we have a Brownian motion, a Poisson random measure, I consider here just a compensated one, so and the Lebesgue part. So then for an adapted Cadillac process eta, we can define the canonical Marcos integral, so of with respect to the semi-martingale parameter, so so phi of xt. So we understand it like this. It's just a definition. Just a definition. So this is the usual part. So this is the Stratonovich part. And here, so in order to deal with the jumps, we have to process the jumps accordingly. But you know, what is the problem here? So what is this? So this fat E, so this fat E is nothing else. So for each jump, you have to do the following. So you have to write the equation phi, so d du phi is now phi of phi r z. So is phi of 0 equals, I don't know, so to, yeah, to something. So, and now, not r, and now u is in the interval 0, 1. And now I denote this bold phi dot rz of something is the solution of this equation at 1. So, and accordingly, I take the initial values and so on. So this means this fat E, so this is not, so it's not the exponent, but the exponential mapping. Good. So, and now we can consider the canonical SDE also. So which will be my characteristics SDE with the generator phi, denoted by this. And okay, so my time is also almost over. I would like, so this is the final thing. So in order to prove this or to justify this argumentation which I gave before, we have to prove the so-called generalized Ito formula for solutions of canonical Marcus SDEs in the semi-martingale setting. So this means I have the same Brownian motion, I have Poisson random measure, and I have two generators. One generator is phi, another generator is psi. Okay. And they all both look like this. So with different, so this is the generator phi, which is given by this with functions f, and phi. And the generator psi is with functions g, large g, and psi here. So, but they have the same Brownian motion, they have the same jumps. And now what I do is I have to solve two canonical SDEs. So one of them depends on the initial value. So this is x of x, the initial value. So they are understood like this. So Stratonovich part, well, in this case, I just removed large jumps. This is compensated small, compensated Poisson random measure. So these are my non-linear mapping which maps jumps. I have a pair of equations, and now I would like to put y into x. So this will be necessary for the proof. And then it turns out, well, I would like to get the usual formula, and you can expect what happens. So of course you have to get sort of a classical formula. So for a composition of two mappings, because as the intuition tells us, so the rules of Stratonovich calculus or of Marcus calculus do not actually formally differ from the rules of usual conventional calculus. So what we expect is that we get x of t or x of y should be given by phi of x of y, and here I have to differentiate, so dx and then dy, but everything in the canonical sense. And I show you the last slide. So this is a short formula which I would like to use or to get, but you have to understand that this formula, so these terms should be, so if you write them in the eta, so as integrals with respect to eta, with respect to Poisson random measure, so they are becoming messy. So so these nice integrals, which formally written with the help of diamond notation, so they are rather long. So, but well, everything is well defined, and so the main idea. So, well, the problem is to prove this formula, but the proof is actually not very difficult, but it's sort of messy. So, as I say, so in order to prove this, okay, so I even didn't write it here. Well, so essentially you have to consider separately, I think, 14 terms in dimension, so in a one-dimensional situation. So, but everything works, and then you're done. Okay, thank you very much for your attention, and well, I think time is over.
Thank you very much for interesting introduction and explanation. By the way, I thought that it is called usually Ito-Wenzel formula when we just apply one stochastic flow to another one.
Yeah, so this is that's a question of notation. So probably it is better to say Ito-Wenzel. Kunita in his book calls it generalized Ito formula.
Okay.
You're right.
Maybe somebody have questions or comments, please.
Just wait a moment. I would like to see the speakers somehow. How to do this?
Jana, I think you must have questions, because it is these approximations are very, very close to approximation of semigroups.
Well, actually, I don't have questions. So thank you very much for a very interesting talk. Yeah, but I need some time to.
I see. Ilya, I have several questions. First of all, as we understand, you don't have to say that your initial condition is a concentration, so it must be -2. So you can consider initial condition from some functional space, and from this point of view, maybe your solution looks like action of some operator random operator semigroups on the initial condition. In this case, I think that your representation related to Marcus integral is more or less a representation of stochastic semigroup, like Skorokhod did, as a solution to stochastic differential equation, even with jumps. And actually, it can explain why you get exponent, because when we consider stochastic exponent of the martingale which have jumps, we get exactly such formulas. Yeah.
Maybe yes, maybe not. So, well, I think generally yes. The question is, what do you mean by the exponent? If you may mean this fat exponent, yeah? Well, this is
Yes.
an exponential mapping in the sense of semigroups, indeed, yeah. So this is not a stochastic
Yes, exactly.
exponent.
No, yes,
yeah.
I said stochastic. Yes,
Yeah,
this is
stochastic.
related to the stochastic exponent of the martingale from Lie algebra when we move it to the Lie group, and then so you start from the operators related to your integrals, like linear operators when we have just dw, dt, dz when you have a Levy process. Then you can consider it together with vector fields like an elements of Lie algebra, and then move it up to by the exponent mapping to Lie group. And in this Lie group, if you initially in Lie algebra have some jumps, you will get this exponents of the exponent mappings. Yeah, exactly the mapping up.
Yes, Andrei. So I think this is yes. I think this is correct. Yes. So yes, probably it should be just somehow written down in well, in big generality. So this is
because I think that there was a good paper of Holevo related to Levi-Hinch representation of Levi processes in Lie groups.
Okay.
So maybe it can be useful just to have a look on it in relation with this transport equation.
Yes, yes. Thanks. So I didn't know that paper by Holevo. I have to. Yeah, I will find it. No, but so this is a very. I think this is a very,
it is like
point, yes.
it is printed in Indian journal Sankhya. I think it was 1976 or something near this data. Sankhya. And other question is the following. When we consider Stratonovich transport equation, actually we can define all this Chern-Strichert representation from Bowden book related to geometry of stochastic flows. When you have like signature of Brownian motion in again in Lie algebra, and then you can find some properties of the equation just using this representation. So it seems that it will be very good to have the same for transport equation when you have vector field with Levy process.
Yes, so I also agree. So yeah, so I have nothing to add. So this is exactly so. There are different approaches, and essentially, so the general feeling and the general intuition is, so if it works for Stratonovich, then it will work for Marcus. So no question.
So it will be interesting. It will be interesting.
So this means, yeah, what is missing is that, well, you have to sit down and and do this. So, but yes, I have no doubt that it works.
Okay, thank you. And some other questions? If there are no other questions, then we finish our work for today. We just have to thank Ilya again for coming and to give an interesting talk. Thank you very much. And we hope that it is just first talk of you at our seminar, not last one.
Okay, yes, thank you very much.
And our next speaker will be Jasmina Georgievich. She will take about our joint work with her about backward stochastic differential equations with interaction. Thank you and bye for today.
Okay,
Bye.